notes from the Cabell House. It's great right there. Very excited you all can be here. We have some important dates coming up. The next notes from the Cabell House is Dr. Dennis Blanton's going to talk about archaeology. That's going to be on November the 7th. Our annual Christmas holiday house tours. I know you all want to go to those. Those are on December 7th and 8th. If you are not yet a member of Historic Stanton, I encourage you to join Historic Stanton. And all it takes to join Historic Stanton is just make a donation to Historic Stanton Foundation. You're a member.
When is the house tour?
Oh, December 7th and 8th. So put that on your calendars, December 7th and 8th. You should be getting emails about that. If you're a member of Historic Stanton, you're getting all these emails, invitations to our special events like this, and invitations to potentially to an archaeology day at the Cabell House that we're still trying to get the date for. So there's a lot of reasons to be on our email list. So there out front there was a pad for you to sign up and join Historic Stanton, and we can use your support for this. The annual meeting, if you're a member, is going to be January 26th. If you're going to put that in your calendar, Sunday, January 26th. That's our annual meeting. And then the notes from the Cabell House will probably start back in February or March of next year. So this will be the one next month will be the last month for this year. So this stuff is really cool. I got to go out with Mr. Rourk when he was setting up at the site. So he has a background in archaeology from Virginia Tech, architectural history from UVA, 25 years experience in 3D modeling, 10 years experience with 3D data. I'm currently the 3D technology specialist at the University of Virginia Library. Work focuses on teaching and research in the Department of Archaeology, Architectural History at UVA, and I think is maybe a nationwide leader in this idea, 3D cultural heritage informatics. This is fascinating stuff. He'll explain it, but this gives you basically a 3D copy of your building, your landscape. So it's really interesting stuff. I'm going to welcome Mr. Rourk. Thank you so much for coming.
Cool.
I really appreciate it.
Thank you. Thank you. I'm a professor at UVA, and I have a professor's voice. But if you would rather I use a microphone, I can do that. I think it'll be a little too loud, though. So can everybody hear me okay? Is this okay if I just use my regular teaching voice? Cool. Thank you. I'm actually, I went to Virginia Tech for architecture, but when I went there, I was undecided for a couple of years, and they asked me what I wanted to do, and I said, I want to do archaeology. And they said, we don't teach that here. And I said, okay, well, I'll do architecture. So I want to thank Frank Strassler for having me here today. I want to thank the Historic Stanton Foundation for having me here today. I'm very excited to be here. I love Stanton. Any reason to come to Stanton is a really great reason. And so coming here to talk about a project that takes place here is even more exciting. So I've got a lot to show you today. So I'm going to go ahead and get rolling. I'm going to give you a crash course in 3D cultural heritage informatics, what that's all about, 3D data. I'm going to keep stressing what is 3D data because it's new to a lot of people. It's new to a lot of professionals in my fields. So I will reiterate things over and over just so that we have somewhat of an understanding of what 3D data is. So I'm going to talk about what I do at UVA as a 3D technologies and data specialist. And then I'm going to talk more specifically about the Cabell Log House project, which took place earlier this year in March. A really fascinating project, and I think you're going to like this. So on a lot of these slides, I provide these QR codes. And QR codes are a way that you can use your phone, flash your camera at the phone, and bring up a website. So there's a lot of additional information that I have up on the web that you're more than welcome to work with and interact with as I'm talking along. I can also provide a list of URLs after the talk for a lot of the interesting things that are up there that are relevant to this work that I'm doing. So at UVA, I'm located at a World Heritage Site. The Academical Village, which includes the Rotunda and a number of pavilions and student rooms, was built starting in 1817 and then mostly built in the 1820s, and is considered a World Heritage Site. So it's recognized as a historic place within the world. So we are surrounded by a ton of history. And as an architectural historian, I feel like it's my duty to try to record that history so that we have a record that I can then put into the library as my role with the library, so that you can get to it, so that future generations can get to it and be able to use this information to understand buildings as they stood not only 200 years ago, but as they stood today. So I'm going to talk about what it is that, that is involved with 3D cultural heritage informatics. So informatics is the study of data. And the way that I describe 3D cultural heritage informatics is it's the collection, processing, and creation of knowledge assets from data, from 3D data. So that's data that is collected using 3D instruments like scanners, 3D laser scanners, 3D structured light scanners, different types of scanning technologies that help us acquire information about the geometry and color of an historic object or place. And so we can record the geometry and color of artifacts, of architecture, of archaeology, and then we have a data set from that acquisition of data, of information. And the data that we process can then go into the library so that you can get access to it. In this slide, I'm showing two different types of data acquisition, okay? And this is what I'm mainly going to be talking about today, is laser scanning. And laser scanning it's a survey technology. It's a way of measuring places and objects in 3 dimensions. So you can think of this laser scanner as a box with a laser in it, and it sits on a tripod. It's about this big, and it sits on like a camera or photographic tripod so that I can move it around spaces. And basically, the laser shoots out of the box, and wherever the laser hits a surface in real space, it creates a point in 3D space. So it creates digital points. And so the laser is going out and it's hitting points all over the surfaces around the scanner. So if I was a scanner, everything I see right here would become 3D data. So we're capturing points of data. And this body of data is called a point cloud because it looks like a big cloud of points. You're going to see some point clouds in a little bit. Actually, what you're looking at right here is a point cloud of Pavilion 3 in the Academical Village. This is a point cloud of some archaeology from Pavilion 4, from Ravenna archaeology, where they found a well structure. And here's a real photo of it. Here's the data of it. So the data looks like the real thing. It's not trying to be a photographic image of the real thing. It is trying to capture the geometry of the real thing through this acquisition of points. The thing is, though, with all of these points, I can measure between any 2 points to get dimensions and get scale. It's like taking a tape measure and measuring infinite times over a space and recording all those measurements into a body of data. And we're getting all of that data instantly with a laser scanner through that process I was just describing, where the laser goes out, hits a surface, creates a point in 3D space, and then we have a body of data known as a point cloud. I also teach how to scan artifacts, and we're using a different kind of scanner here. This is a handheld scanner using a technique called structured light. And with structured light, it's a little different from laser scanning. Structured light uses a pattern that's flashed over the object, and this is a Cypriot piece of Cypriot archaeology from the Fralin Museum of Art, which is our museum at UVA. Cameras on board this scanner will watch how that pattern deforms over the object and be able to create very high precision data. And this is what the most important thing is that we are trying to collect and process high precision data so that we are replicating the real thing as precisely and as closely as possible. That way, when you use it for your research, or we have the scholarly community downloads and uses this, they will be working with the actual object, with the actual building or place. They'll be able to measure it in many different ways. In laser scanning, we can scan to an accuracy of 2 millimeters. And that's pretty good for a scanning technique that can possibly scan hundreds of acres, which we have done in Italy. We scanned 100 acres of the cultural landscape around the Villa La Rotonda in Vicenza. And that was a very large data set. But we can scan, we can get measurements down to 2 millimeters. That's the joints between bricks. So we're capturing very high precision data. With this structured light scanning technology, we are collecting data that is sub-millimeter. So we're getting into the micron level of collecting data about artifacts, down to about 0.2, and I have a new scanner that will go to 0.1 millimeter, so 100 microns. And that's, yeah, we need that precision so that I can ensure that when I put this up in the library, you can depend on the accuracy of this data. So it's all about precision of data. That's the most important thing for me acting in my library role, as well as my architectural history role. I bring this up because there's another really fascinating way of collecting 3D information using 2D images, and it's called photogrammetry. And with photogrammetry, you can take photos of an object, and then you can convert those photos into high-precision 3D data so that you can replicate that historic object or that historic place with just camera photos. And I was trained to do this, so I was trained to do this at really high precision using very careful photographic techniques. Of course, here I am in a hayfield in Tibet where I did my field research, and I'm taking photos with a point and shoot, but it's a very nice point and shoot. And the idea is going around the object, taking a series of very carefully taken photos. And with this kind of data, I'm able to replicate the straws, each individual straw in this hay bale. And that's how precise this kind of technology can be, because it's very difficult to haul laser scanners around in Tibet. They don't like that. But cameras, no problem. I can go all over the place with cameras. We can also put cameras up in the sky with drones. We can send a quadcopter up with a high-definition camera, and we can take lots of photos of a whole site, of a whole building, and recreate that site and its landscape and the building and roof structure using a series of photos, which we have done right there with the McCormick Observatory, which overlooks the University of Virginia up on Mount Jefferson. Everybody knows it as O Hill. So those are some of the techniques, and again, I'm going to re-emphasize that I am collecting point data here, point data and color information. And this is what it looks like. It's just 7 values of numbers. It's an XYZ point in space, it's an RGB value, and then it's another value that tells how light hits the surface so that we know how to see the color on the surface in 3D. It's just 7 values, but it's millions and sometimes billions of lines of data for every single point that's collected from the historic place or object. And in this case, I was scanning the aviator statue, which sits between our 2 main libraries on grounds, the now Shannon Library and Clemens Library. And I just moved from one to the other, and I had to pass by him quite a bit. This is a statue that was created by Gutzon Borglum just before he did Mount Rushmore. And it's kind of a symbol of the library since it sits between the libraries like that. But you can see here that I've just collected just a ton of points. And sometimes you can connect the dots and the points and create what's called a solid model. And that's the kind of 3D that a lot of people are more familiar with. But I just want to emphasize, we are talking about data. These are not modeled from geometry like you hear with a lot of 3D modeling, and in my world, a lot of CAD, architectural modeling, things like that. We're modeling from either standard geometries or organic geometries, geometries. We are actually recording surface information of the original. So this is not conjectural at all. This is the original real thing. And then comes the processing phase. So like I said, in informatics, there's collection and then there's processing. And during the processing phase, we want to make sure that we're bringing together data sets and fusing them together as precisely as possible so that we are faithfully reproducing the original subject matter. So when I'm out in the field and I'm trying to record a building such as the rotunda here, I have to take a lot of different scan positions, right? Because if I scan right here, I'm not seeing what's out in that hallway. So I have to scan out there too. I have to scan out that door over there and up the hallway and out the door and the whole building going all the way around so that I have a whole bunch of different scan data sets that need to come together in the processing part of informatics. And in that processing, we call that registration because we are registering two different data sets together as precisely as possible so that we have reconstructed or processed the entire building and faithfully brought it together so that when you measure this pediment up here, it's exactly the distance of the real pediment. So we want to make sure that you are getting precise measurement from this information. Same thing with artifacts. When I scan an artifact, I have to scan one side of the artifact, and then I have to flip it over and scan the other side, and then I have to bring the two pieces together and fuse them together to make one artifact as faithfully as possible. And then once we have that, we have a faithful piece of data that we can then put up into the library. Same thing with photogrammetry. We want to make sure that the photos are clear and we have enough overlap between the photos so that we can recreate the subject matter as faithfully as possible. Like this 18th century gravestone from Dromahair in Ireland. A nice little cemetery built by my forefathers in the 16th century. Once we have the data processed, we have one comprehensive data set that describes the place or the object. And then we can do a whole bunch of different things with that data. We can bring it into CAD or BIM. Building information modeling is what architects use nowadays to build 3D models of buildings so that they can study the building over time. They can record all the different elements of a building throughout the life of the building. And a lot of times these days, the recording of the life of a building starts with the point cloud data. So we bring in all that 3D information, we can model over top of it, or we can test your CAD model to see if it's accurate. Because if there's a column in your CAD model that doesn't match up to the point cloud model, the point cloud model is not wrong, your model is wrong, and you need to fix it. So we want to make sure your building is going to stand up straight. Also, in CAD modeling, there's a lot of conjectural modeling. There's a lot of using perfect geometries to describe perfectly rectangular and plumb walls. There is no such thing as a straight line in history. All historic buildings have wavy lines all over the place. And 3D modeling will record, 3D scanning will record that so that we have a record of the real wall that's going to wave all over the place. And that's good to see because then maybe if it's waving a little too much, you might need to go in there and shore it up and find some sort of structural solution to it. So it's good to be able to mix that in with your architectural modeling. We can also extract elements from the point cloud data. And like I said, you can take all the points and you can connect the dots and you can create a 3D model out of it that can then go into a bigger architectural model, like this model of Pavilion 3 at the Academical Village. And what we did was we were able to extract a Corinthian capital. And if you can imagine trying to make one of these out of some 3D geometry, it's pretty hard to do, and it would take a very long time to do it, whereas we were able to just pull this right out of the 3D data, mesh it, and then throw it into this CAD model over here. So it really helps speed up time. We can also 3D print things. We can take these elements and 3D print. This is that same capital that's been 3D printed. Here's a flock of birdmen, of aviators from that aviator scan. We can also create models that you can interact with on web pages or in other interfaces that allow you to interact with 3D, such as virtual reality. And I'm going to show you a little bit more of this later on with the log cabin, but we can take the raw data and put it directly into virtual reality so you can walk around an historic place. And we have a number of these historic places in our public VR labs at the university libraries so that you can go in there, the public can go in there, and they can go and interact with real historic buildings and be able to walk around inside of them at a one-to-one scale as if you were actually there, immersed in this building. And so you can see we have a couple of labs that we have in, actually in Shannon Library and in Clemens Library. We also can do augmented reality. And augmented reality is where you can use a device like your phone or special goggles to see 3D in the real world. So I can take that aviator statue and I can place it right here in the middle of the floor and I can see it either with my phone or with some special goggles. And there are a lot more goggles coming out there these days to be able to see that. And that way you can interact with history directly, maybe in a new context, maybe in a new place, maybe in the original place where something once stood and no longer does, if you've scanned it before they've taken it down. So virtual reality and augmented reality are powerful ways that you can interact with 3D. So we've collected the data, we've processed the data, and we've created knowledge assets of the data so that that data can go to the library. Why do we even do this? Well, we learned a lesson about a little over 100 years ago, actually it's coming up on 130 years ago, where the rotunda burned down in October of 1895, just before Halloween. And it was a terrible fire, and it burnt, I'd say, 80% of the original rotunda, Jefferson's Rotunda, burned down. We lost a lot of historic material at that time. And what we're finding is there's really not a lot of architectural documentation of this historic building. It's a World Heritage Site. There's not a lot of architectural documentation that's that detailed of the original rotunda. There are some basic architectural documentations that everybody has seen, but none of the real details. If we had 3D scanned this, we would know precisely what the original Corinthian capitals, which we've lost all of them, we don't know where any of them are, what they were, what their scale was, what their geometry was all about. If we wanted to recreate one today, we could do that with 3D data. But we didn't have that, of course, back in 1895. We do have this now. And so that's why I feel like it's my job to go out there and record as many buildings as possible so that we have this data. And then fortunately, even though I'm in architectural history, I'm also fortunately with the library, and the library is harvesting all of this information and making it available to you in the community, in the scholarly community. I do this through a spectrum of preservation, of asset preservation. And I describe that spectrum of preservation as, on one end, we have the dark archives. We have archives where you're going to put data, and it's going to be there for the next 1,000 years or more. It's not the data that you're going to go and pull right out immediately and work with. It's being put into this archive so that future generations will have it. It's ensuring the life of this data and this information. And we use the AP Trust, the Academic Preservation Trust, which is housed at UVA, to do this. And the AP Trust is a community of institutions that have subscribed to this trust, and they are taking all this information and storing it away redundantly in different places across the country to make sure that this data stays around for a long time. On the other end of the spectrum is open access. And at the UVA library, we are an open access library. We believe that everybody should be able to get to information and be able to do whatever they want with it. That is the scholarly approach, and that's how scholarly efforts are propelled forward. And so on our end, I use a platform called Dataverse, which is open source out of Harvard. A lot of institutions subscribe to Dataverse, just like they do with AP Trust. Dataverse will upload just about any format. And I work with a lot of the strangest formats that nobody's ever heard of. And Dataverse will take all those formats of weird data and put it up there. And not only the raw data, but I'm trying to export out files that I feel, or that the communities that I interact with and communicate with feel will be around for a number of years. So we want to make this data available now so that you can download it and 3D print Corinthian capital if you want to in chocolate. And also be able to get to this in the future with human readable, easily text parsable formats that if these formats aren't alive in another 100 years, they'll be easily changed into formats that will be out there. So you can immediately get to this information now. At UVA, we put things into Dataverse, which is a part of our Libra open access platform. And the data, some stuff goes on in the back end that I have nothing to do with, that our brilliant programmers take care of. And then you can search and discover this on Virgo, which is where you get books, periodicals, and now 3D data. And so you can go to Virgo and you can search for, the 3D Cabell Log House and you'll find it there, actually. And we'll take a look at that. Spoiler alert. And then, of course, I teach this in architectural history with my colleague, Andy Johnston, who is the director of the program in historic preservation in architectural history at UVA. And each semester, I take a group of students out into the field and we go on adventures and we scan a lot of historic places. We work with a lot of artifacts. I have connections to a lot of different artifacts collections throughout Central Virginia, including the ones with not only the Fralin Museum of Art on grounds, but Montpelier, Monticello, and I work a lot with Ravenna archaeology, as I had mentioned before, trying to scan these artifacts so that we can get them into the library and they will be there for research and pedagogy. And for me, that is my pedagogy. And you can see here, we go to a whole number of places through here, and you can see their adventures if you follow that QR code. I have the students create portfolios every semester. And so you can see some of those portfolios online at that website and be able to see the kinds of places and things that we are working with. So that, in a nutshell, is 3D cultural heritage informatics. And now, for something completely different. Now I want to talk more specifically about the Cabell Log House, which I had the opportunity, thanks to Frank Strassler, I had the opportunity to come out and work on site last March. It was a perfect day to go there. None of the critters were awake yet. The poison ivy was still a little down, low on the ground. The spiders and the bugs hadn't quite come out yet either. These are all things you got to think about when you're crawling around under a 200-year-old house. But this was a pleasure to be able to work on site here. Here we see the real house, but on the back end of it is all point cloud data. That's all part of the point cloud data that I collected on site from that day in March and was able to put together using 3D cultural heritage informatics. I scanned the site with a number of the laser scanners that I was describing earlier, and we're going to see that in a minute. And I also learned a lot of interesting things about this house. The house was built in 1869, thereabouts, by Edmund Cabell. And it was in his family into the 20th century until I think Historic Stanton got it. and then gave it away, and then got it again. And now they have it. It looks a little rough on the outside, but inside it has really good bones, and underneath as well. And hopefully you're about to see that in some of these renderings. I have also built a website on this entire adventure of scanning and processing and producing a lot of assets that you're about to see here. There are a lot more things on the website that you can interact with. So feel free to definitely take a look at that and follow along as I talk about this. And I use ESRI or Esri story maps, ArcGIS story maps to do that. My group that I work with, the Scholars Lab in the University of Virginia Library, we host all of our GIS materials. That's map making software and things like that that everybody in the university is using. And there's a really great free tool called Story Maps that I teach the students how to use because it's very easy to work with. And we can incorporate 3D objects and things like that in there. So if you go back to that pedagogy page, you'll see some 3D objects that you can work with. So starting with the informatics process, first thing I need to do is a site review. I need to go through the site to understand the scope of everything that needs to be scanned. What are the geometries? What are the details of history that need to be recorded when I'm going to put scanners into this place and move it all around? Recording these details is very important, like the interior structure down here, this raw, rough wooden pegged structure in the roof over here. There's just so many great details of construction in this house that the 3D scanner needs to be able to capture. And even crawling underneath. You got to crawl underneath a lot of houses to make sure that you get all the details. And most of the details are under a house or up in the attic, because that's where you see all the structural things going on. There is no power at this site, so I had to set up a generator, there's my lonely little generator right there, so that I could light up this space. And when you peer into a dark attic or a dark basement at first, it's very daunting. You're not quite sure what's going to jump out at you, but when you light it up, it feels like a living room. So it's a whole nother space once you light up these spaces and you enter into them and start to collect all this information, and they become a lot friendlier. And that's important because those spaces are extremely important. And then comes the data collection. So then that's where I have to move all around the site with the 5 scanners that I have and take laser scans from all of these different positions. So I have one scanner, I think at least one, going all around the exterior of the house. Actually, I had two different scanners going on. And taking scans of the whole exterior, going all the way around. Vegetation can be a problem sometimes, so you got to figure out how to work a scanner in between the vegetation to be able to get all those surfaces. And then scanning the interior. I had a couple of scanners going on inside the house, the main floor of the house, making sure to get all of the rooms in there. And usually I have to take at least 2 scans per room to make sure that that room is completely scanned. But a lot of times it takes more than that. It can take 3 scans depending on how complex that space is. And we want to make sure that we get all of those spaces recorded. Even putting a scanner out on the roof so that we get that roof information. This is a rare opportunity because usually I can't get rooftops as well as I would like. If I'm down on the ground, I have a scanner that's looking up, and if I can't see the roof from the ground, then the scanner's not going to get that information. And that's where we might bring a drone in to do photogrammetry of the site and get photographs of the rooftop, and then we can combine that with this laser scanning data. But at this point, for this project, the roof was at street level on one side, and then I was able to get right out onto the roof from the attic on this side. So got a lot of really great roof data just from the attic space. And then, of course, there's crawling around underneath the house, which was fascinating, actually. And I was so surprised by how well constructed things were. There was a lot of new construction down there, but it really gave me a lot of confidence in the structure of the main floor. It's extremely sound, very well built. And these scanners helped me record all that information so that I've got all the joists going through here and how they connect to your foundation walls and all that sort of thing. And I mean, these are difficult spaces. There were spaces towards the back that were difficult to get, that you just can't get because there's just not enough room. So you do the best you can. You get as much information as you can with the space to put a scanner into. And then there's the processing phase of informatics. That's where I'm bringing together all of these data sets and registering them together, trying to bring them as close together as they can. This is the actual software I use. It's built by Faro, who make my scanners, F-A-R-O. It's called Scene. And in here you can see each one of these is a scan data set. So these are all different positions I took from around the house to be able to effectively document this house and bring all of these data sets together. And when I'm bringing them together, I can check numerically how close they're coming together by these reports that come up after I do a registration, so that I know, I have confidence that this data is coming together as precisely as possible so that I'm giving you good data when you go and download it from the library. And so this is kind of the whole data set in itself. These are some stats on that. This is the extent of what I scanned. This is everything I scanned. This is the house right here. You always get more data than you ask for when you're scanning, because the scanner is scanning in 360 and it can scan out to a great distance, okay? An effective distance of about 25 to 30 feet, okay, in diameter, but it's actually, it can gather data from objects that could be 100 feet away. So that's why I've got way more data in here than I really need to work with, okay? Again, that's our house and immediate landscape right here. And you can see I took 44 scans to record the entire house. I started at about 9 or 10 in the morning, and I was done by about 5 or 6 in the afternoon. And it was just me. I didn't bring students out to this one because it was kind of towards the end of the semester and everybody's busy. But we have 811 million points of data that recorded this space. And that's a lot of points of data, especially for a smaller building like this. So you can imagine the amount of data that I probably got for the rotunda. It's well over 1 billion points of data. That's big data. This is big 3D data, because that's a lot of points between which any two of them you can find dimensions. You can make measurements and find dimensions. So that's a huge data set. So I don't want to work with all this data here, though. That's a little too much data. So I need to use what's called a clipping box to only confine to the data to what I really need to work with. So I can use this box to hide all the other data that I don't really need. And then I can export this data out to some sort of format that I can then bring into other software like CAD software or 3D modeling software. For me, I bring it into another piece of software that allows me to do some more editing and optimization of the 3D data, and then I can visualize it in a whole bunch of different ways. So you don't want to work with this huge mass of data. You want to confine it to just what you need to work with. And so then, once I have that data refined, optimized, edited, cleaned up, I can then start to visualize it architecturally. So I want to visualize this data the way that architects would, using perspectives, plans, sections, elevations, isometrics, axonometrics, all these kinds of visualization tools that architects use to be able to communicate forth a place and a space to the public. And so here we have just a whole series of perspective shots of renders from using a virtual camera that I can place anywhere in the site. So I'm not up in the air. I didn't go up in the air, but I can put a virtual camera up in the air in the 3D software, and then I can get a bird's eye view of this without actually having to go into the air myself. And so we have elevation views here in perspective and just some basic perspective views to understand the site. And then I want to render out some of the interiors so that we can see what's going on the inside. Again, this is not photographic quality. This isn't supposed to be photographic quality. This is a model of data. This is a data model. And so it shows me all of the structural elements in here. It shows me where these structural elements come together, how the whole building comes together as a structural architectural composition, and then I can measure between any 2 points in here to be able to get those dimensions. So I have some shots here from the main floor on these levels, and then from the attic up in that level, because we scanned everything. We moved the scanner, I moved the scanner all over the place, and got this information, including the scary basement, which wasn't so scary once I lit it up, and including some of my wiring in here. And again, this is not photographic, but it does show me where all the structural members are and how they all come together and what their dimensions are. And then I can visualize these things architecturally using orthographic views. Orthographic view is where you take out perspective distortion. In perspective distortion, you have your points are fading off into the distance so that the objects closer to the camera look bigger than they do as they fade off. In orthographic views, the front and the back are at the same dimension. So we can see things at scale, and we can understand architectural composition and scale and ratios more clearly that way. We can also take that clipping box that I showed you earlier, and we can clip out some of this information so that we start to look through the data set. We start to look through the house. So I've cut the house in half here, and I'm looking down at the attic level, and you can see here I've got this big void. This is the chimney. I can't scan behind the walls, okay? I'm scanning the surface of the walls. And so if I scan on one side of the wall and I scan on the other side of the wall, that void you see is the wall. We don't scan inside the walls. That's a technology called tomography. That's what ground penetrating radar can do. That's what X-rays and MRIs do. I actually do have ground penetrating radar that I can use, which I've been using at cemeteries and archaeological sites, but does not give you the clarity of information that topographic technologies such as laser scanning give you. So I'm just scanning the surface here. But by scanning the surface, I can reveal what's behind the wall. And then if I compress my clipping plane, so I'm slicing through the building, a very thin slice, I get a plan of the building, okay? And you can see this looks like a straight line, but it's not really. If you take a straight edge or a virtual straight edge through here, it's waving around quite a bit. And I'm sorry you can't see these, but these are all dimensions of these spaces. So I can click on this wall here and that wall there, and I can find out what's the width of this room. What's the width of the entire building? What's the width going this way of the building? What are the dimensions of that masonry chimney block that goes up through the middle of the house? I can find all of those dimensions now because I can measure between any two of the points in this data set. So I refine the data. I refine the way that I look at the data so that I'm looking just at part of the data, the most informative part of the data, which is constricted by a clipping box, which reveals these plans. And this is a plan that you can then bring into your architectural information. And then I slice the building right down the middle, right through the chimney. Here's an elevational view of it. This is just looking straight on in orthographic view of the main facade as you go through the porch here. And this is looking at the main level through here, the attic level through here. You have the chimney going up through here. And then if I compress that view even more, I get an actual section through the building. This is an architectural section through the building that allows me, again, to find any dimensions that I want to anywhere in this building, almost infinite dimensions. When we draw these, and I've hand measured buildings before using tape measure and graph paper and a pencil, and it takes forever to do that. And when you do a section drawing on ink and vellum, which was how I was trained at Virginia Tech many years ago, you're usually focused on one slice through a building, right? And you spend hours painstakingly drawing this by hand on vellum so that people understand the section through the building. Here, I can pull a section out of this data set anywhere along the length of the building, anywhere along the plan of the building, almost infinite sections through there instantly, and find dimensions like that, and then render it just like this in a matter of minutes, and then you've got all this information. And then I can take this and I can draft over top of it if I want to make clean architectural documentation out of it. But this right here has a ton of information to reveal in its own. And here's another section looking lengthwise through it. Again, looking at the elevation, here's a section through the building, and then we have another compressed section showing you the wood stove up in the attic and the chimney block going through here. This is all chimney masonry mass that goes down to the ground floor in the basement. You can see how high that is. I was on my hands and knees for quite a bit of that. And you can see this floor. Does that look like a straight line? We can't draw that as a straight line. And yeah, you need to know where it's sagging so that you can fix that, right? You might need to put some more support through here, or find out why are these structural members right here failing. We can look at that. You can look at this and then go back to the site and look at what's really going on and say, oh, well, it's because this structural member is split all the way through, and it either needs a sister joist or it needs to be replaced. So it reveals a lot of information. And then we can take all of this information and put it together into an animation. And so this is a way that we can combine all of those still rendered images into a tour of and it's stuttering, of course. But it takes you on a tour through the building so that you can understand how all those static images come together and are rendered. And this is up in the library too. I have a higher resolution version of this online that you can access from that website that I gave you the QR code for. So this is all up there if you want to take a look at that. But this gives you a really good idea of, again, the site review, looking at it in perspective, even going down into the scary basement. So you get to move through it here, and you don't have to get your hands and your knees all beat up and move through there. It wasn't that bad, actually. Like I said, when you light it up, it becomes a much friendlier space. And now we're going to view this architecturally. So I've compressed out of perspective into the orthographic view that I was talking about, flattened it out so that we can look through these buildings architecturally, through elevations, through sections, and then dimensions, using dimensions to understand the scale of the building. And it's nice to see this all come together as a moving entity. Going through the kitchen annex, through the main building. And of course, on the video, if you go and visit this, you can stop the video and take a look at this. The longer I render this, the bigger the file size for putting this up on the web. So that's why I kind of have to move through it quickly. Oh, actually, you can see the dimensions much better in the video. Wow, that's cool. And there we have a nice rendered plan and down to that's the floor structure. This is all the floor structure because I've recorded all of the joists underneath the main floor. And then there's the basement ground level as it's flowing up the hill. And we can get all sorts of dimensions out of that. And then back to perspective. And then, one more thing, and one more thing. There we go. I have this running in virtual reality in my section of the library, which is in Shannon Library, in the Scholars Lab. We're on the third floor, east wing, overlooking the rotunda. And we have a public virtual reality lab there so that and I have a whole bunch of historic places loaded onto our VR machine, so you can just go in there and walk around these spaces. So I took a VR tour of the house, and really more architects should be using this, because this is a way to immerse yourself in a building and be able to study it up close at 1-to-1 scale as if you're there. Now, getting your client to go into virtual reality might not be too practical, because you kind of look a little silly as a spaceman here with your goggles on and things like that. But virtual reality is becoming cheaper, it's becoming more powerful, and a little bit more chic as those goggles start to slim down. We're not quite there yet, but we'll get there at some point. But it is a really great way to visit a space, be able to walk through it. You can see here I can get dimensions as I'm walking around the space. I can just point at the floor down here, pull a vector across, and get the dimension of that floor as I'm standing on it. Or anything, really. I can find out what the spacing is here on these structural members, either in the wall studs or in the joists overhead or the rafters up in the attic. A whole bunch of different things. So there's a lot of things you can do with the 3D data. Just a number of things. And there are more things that are happening with 3D AI. I'm just going to slip that in there real quick. But 3D AI is becoming an extremely compelling way of visiting sites. You can use cameras, or you can use a free app on your iPhone. And by the way, if you have an iPhone Pro version 12 or more, you have a LiDAR sensor on here, and you can scan with this. You can scan with your phone. I use an app called Scaniverse because it's free. And if it's free, it's for me. And it does a very high resolution scan, but it also works with 3D AI these days in a process that's called Gaussian splatting. And it's where you train your camera and the LiDAR to look at a space, and it will recreate it photographically so that you can move through that space photographically with that sort of intense visualization. And that's where things are going these days. It's not going to replace what we have here, because it's not a body of data. This is data, whereas that is a photographic visualization. And we need to keep remembering the difference between those two and how important the data is. Because with the data, you can do anything. And then you can also access this data. I put this data up in the library so that you can download it if you want to in different forms. Actually, it's not there yet, because we have a new system of uploading that I'm still trying to get acquainted to. So it'll be up there soon, but you can always contact me if you want the data, and I can get it to you. I can talk to you about how you would use it, all those kinds of things. So it might be helpful with the reconstruction efforts, because an architectural team can use this. They have used other architecture firms have used my data before, gotten it from the library, and been able to use it for historic structural reports, or HSRs, to use in actual reconstructions or renovations, those kinds of things of historic buildings, so that we can be mindful of all the details of history that need to remain, because that's super important, because all those details are part of the historic narrative of a building. And the building's historic narrative is the narrative of the people that built it and that lived there. And that's super important that we keep those details preserved so that we can learn all about them. And I love this picture because it's that reminder that this is why we need that data. Because we don't even know, that building's completely gone. that you're looking at. And this is, this part is gone, and this is all that was left of the rotunda, was that tiny spot back there. And if we had 3D scanning, we could rebuild the entire thing if we want to. So anyway, that's all I have to talk about.
I told you that'd be really interesting. You guys got any questions about anything to do with the work he's been doing, or about over here? Oh yeah.
I've got one question about, do you all have a relationship with laser scanning with the tabs, the Storm Urban Building Survey?
That's a great question. This past summer, I got to spend time with Mark Shara, who he runs the field training schools for HABS. HABS is the Historic Architectural Building Survey. It's the National Building Survey for the Library of Congress. If you go to HABS in the Library of Congress, you can find architectural information for a lot of buildings. I actually have hand-drawn ink and vellum drawings in HABS, but I don't have any 3D data up there yet. But this data is available in the library, so if they want to bring this down and pull this into HABS, they could. HABS is a little bit behind right now as far as directly using 3D data like this as a main data set. It's usually ancillary to the traditional type of documentation, which are your architectural sheets, right? So you need to have that information first, and then the data set comes in after that. But what Mark is doing with his field students, they do a combination of laser scanning and hand measuring of buildings, and then they translate all of that into drawings for a particular building. And I was able to hang out with his field school on a couple of occasions this past summer. And that is really the goal. The goal is to get to that level of documentation. I don't have the time or the resources. I'm the only person at the UVA library doing all of this. But it's my wish that at some point I can train students or have students take this to the HABS quality architectural documentation that it needs to be. That's one step beyond. Very good question. Yeah.
What was could you repeat the name of the scanning thing you said for LiDAR on the iPhone?
Yes, Scaniverse. Scaniverse. Here, I'll see if I can bring it up.
You gotta get a new iPhone, huh?
This is that website, by the way.
You need a pro. It's like, why do you need a pro? That's why.
And I can do a demonstration after all of this, if anybody's interested, how this works. I teach it. You can use iPad Pros for this as well. And it will do LiDAR scanning in addition to 3D AI. So either or. Really powerful. Yes?
Minor detail, those windows in the basement, which presumably were originals, in your scan, do you think you got enough details off the windows, to pull out the window itself as a little 3D model, or would you have had to scan them separately?
Is this the window that's on the ground, or windows that are...
Two windows on the ground leaning up against each other?
Yeah.
I'm just curious, how much extra effort you would have to make.
I have to go back and take a look and see how much data I did actually collect that, because I remember seeing there was a ton of interesting things down in there, and I wanted to make sure that we had that information. If we were going to recreate it at higher definition, I'd want to take them out and scan them, maybe even with structured light scanning. But we probably have the basic dimensions if we needed to reconstruct them. Yeah, that's a good question, because those kinds of details are what we have in mind when we're trying to scan these buildings. We want that level of detail. But remember, we're scanning at 2mm precision. And for very small details, it's hard to get that much information, but we might have enough information to point to something and say, oh, we need to go back and document that a little better. Any other questions? Yes? That's a good question too, because when you get to a space... Oh, you mean as far as buildings go? Yeah, well, I want to scan everything. I get requests like this project. Oh, that thing is flashing around. Let me change this. Sorry. I get requests, and then I have my eye on particular places that I'm interested in. I'm associated with a couple of preservation groups, the historic I'm with the Fluvanna Historical Society in my county, but I'm also with a group called Preservation Piedmont, which works in a more regional area. And so places of interest, and particularly places that are endangered, that are going to potentially become demolished, come up on my radar. And if I have the time and the resources, I'll try to get out there and scan some of those places. I unfortunately see a lot of places torn down that I just don't have time to get to. But it's a combination of information that comes my way and my own interests.
I am curious about something. On one of your slides, you had the numbers.
Yes.
And one of those columns had a lot of pi. 3.14?
Oh, did it? That might have been, that's a great observation.
Is that part of is pi part of just trying to put everything in place? Not really the question, but I don't know how to phrase the question.
Let's see. Let me go from current slide. There we go. No, not really. Well, there's 3.14 all through here. That's not pi though. It's not the. I think after the 4, it's unpi. But no, not really, because we're not doing mathematical analysis of this. Now, if we were doing mathematical analysis of maybe some of the round geometries that we were working with, we might involve pi in some form that way, to find circumference or area or things like that. But the software can automatically find area of just about anything in there that we outline, but not directly. Not directly. It was a keen eye on pi. That's something I will not be able to not see now.
But I also see that it doesn't eliminate people from your scans.
Right. Yes. Actually, if you look, I'm glad you mentioned that, because if you look on the website, yes, yes. Let's go down here, and let's see. Nope, that's too far.
I'm outside on the wall.
Oh, I don't have it in here. I thought I did. Rats. Oh, here it is. So, as part of the process, and I didn't have slides for this, but it's here in the website, I have to go through and delete out data that I don't want. And so I work in a lot of public places, and so I get a lot of people moving through. And sometimes I'll leave them in, right? Like sitting up on the wall. Or actually, there's 2 people sitting at the very corner from that day. And in virtual reality, they're like right there, and they're at scale. And you turn around, it's like, oh, hey. So sometimes it's good to leave people in there because they do provide a scale figure, which is nice. But when, like, this is probably me or one of us moving through the hallway while I was scanning, and it just looks like a blob. And really what we need to be able to see this space here, because this is a major means of egress. And so I actually will go through the data and select out. See, there it is. You can see a little better there. And this is actually interesting because this is someone moving through space as you're getting scanned. So we're actually capturing 4D. And I will select out that information and delete it out if it's in the way of the more important information. But if I can leave it in there, if I can leave you in there, then you become a part of the record that will last for the next 10,000 years. And now you are living history in the library. Yay, library. So not to say that I haven't purposefully scanned myself into a lot of data sets as a scale figure so that they will be able to 3D print me one day. And AI will be able to figure out the intelligence by scraping all of our social media. So that's, I don't want to go that far. Anyway, yeah, that's a great question. Some of the data goes, some of the data stays.
In your 7 columns, on those columns,
Yes?
so you mentioned some of it is in color coordination.
Yeah.
But it's not able to, like on the aviator, the fact that it's bronze or metal, it doesn't tell you the material type, does it? Is it that sort of thing?
No, but that's something I'm really interested in. It only gives you the geometry and the color that the camera picks up. Okay, now that being said, when I'm working with artifacts, like the Cypriot artifact we saw being scanned by structured light, that's a particular clay, okay? That's a particular clay that comes from Cyprus from, I don't know, 3,000 years ago. And there is a device called X-ray fluorescence, or XRF, that a lot of people in museums, especially museums, but in our special collections, for example, can use this device to find out the chemical composition of a subject. So you can point the device at this part of an artifact, and you can find out what's the chemical composition of it, so that you can start to find out what's that chemistry, what are those elements, because one day we'll be able to 3D print not in just stupid plastic, but in actual materials. And if we have the XRF data on that artifact, we might be able to actually recreate that artifact exactly as it was, including chemically. Because we can already 3D print a number of different materials. We can 3D print ceramics that can be kiln fired. We can sort of 3D print chocolate, but it's not that great. So I teach students how to create 3D molds from plastic, and then that's a whole other thing. But yeah, so we're heading in that direction. So, 100 years from now, if we had that XRF information, we'd be able to use that. But again, I don't have time to go out and do that. But if we had a request for that, I would try to get that material scanned by one of our special collections specialists. So a little bit of the future there. Yes?
So could we use that for mortar analysis and the daubing and chinking of the building, things like that, to get that composition?
I'm only speculating about all of this, but I would say I don't see why not. Because that's important too, right? You have, especially in Cabell, my friend Mark Cutney was out there, and he was looking at the materials of it, and he was fascinated by that daubing. And Mark has seen everything out there, and he knows every little detail of historic construction, and he was fascinated by that daubing. So if we could, most obviously that daubing came from site, right? From 1869. Probably the mud out there combined with other elements that were used as a binding agent for putting in between the logs there. So yeah, I would think that you would be able to use it on that daubing and then maybe find a sample nearby and see how it's changed over time, maybe. We're starting to get into geochemical stuff that I don't know anything about, so I'm just speculating. Yes, maybe. Yeah.
Do you ever get requests for like forensics investigations saying, we've got this specific question, do you think you can answer it?
That's a great question too, because this technology is used in crime forensics quite often. Criminal forensics uses the Faro scanner to scan a crime scene, because then you've got the exact crime scene and you can start to figure out trajectories and all sorts of things like that. I don't do that. I was talking to some police out in Fluvanna one time, and I was telling them about the iPhone. And I said, you can scan this. You could scan a crime scene with your iPhone and then be able to analyze what's going on here just from that data that your phone was able to get. And they were like, really? And I was like, yeah, I'll train you guys how to do it. I never heard anything back, but But I think, groups are doing that sort of thing out there. Now, I heard something very interesting the other day on the forensics of plantation culture and looking at plantations as crime scenes because they were crime scenes for the enslaved that were out there. It was a criminal culture. And so there are a lot of details and I've been to a ton of former plantations and scanned a lot of architecture from there. There are a lot of details that go towards helping to understand these scenes as crime scenes and being able to analyze that historically. And now we have the 3D data to be able to try to analyze that as well. So forensics is now starting to go into the cultural heritage historic area a little bit more.
They do have this equipment and they do use it.
Yep. Yep. Yes?
How is your relationship with Farrow?
With Farrow?
Later scanners, do you guys get special deals or do they give you special kitted out stuff or is it primarily commercial purchases and stuff?
No, we get educational discounts. But that being said, I got my first scanner in 2011 and it was $70,000. And so that's part of the training, isn't it? That, yeah, you're handling a $70,000 scanner. And when you do that, you wake up real fast and you're watching everything you're walking around on as you're carrying this thing on a tripod upstairs or into an attic or under a house, that sort of thing. Since then, I have a really great relationship with my rep because we've probably purchased over $250,000 worth of equipment with the 5 scanners that we have and other pieces of equipment. So we get good deals as far as educational pricing goes. We just bought a Leica RTC 360, which is kind of that's the top of the line these days. It's another kind of laser scanner, but it's super fast. It's super expensive. It's $110,000. And I think it's $125,000 for commercial use. And the software is stupidly expensive as well. I didn't know what I was getting into when I got the grant funding to buy it, because now it's difficult to sustain it. I have to pay for warranties and things like that year after year, and those warranties are very expensive. And so that's something you got to think about when you get this equipment. It's not just buying a camera, okay, that you're going to go out in the field and shoot a whole bunch of pictures. You're buying a system that needs to be sustained over time. These things need to be calibrated so that you're making sure that the laser is picking up exactly what it should be picking up. So I send them in for calibration and things like that. And it's very expensive. But yeah, they help me out. They sent me a whole bunch of backpacks one year with their logo all over it. So I still haven't gotten a coffee mug. I'm waiting for that.
All right, well, thank you very much.
Thank you.
If you have questions, we'll have this information on the website up there. Also, Ari Carlos, our neighborhood preservation coordinator, was his student, and so she knows maybe some of this.
All of it.
So you can also reach out to Ari if you have any questions. If you want to come in and talk about what's on the webpage, I'm sure she'd be glad to talk about all that. There's a blog that we followed up on the webpage, and the video will be posted on the webpage, and the webpage that Will mentioned earlier, that'll be linked to on our webpage as well.
Cool.
Afterwards. So it's all be out there. Share with your friends, pass the word, fascinating stuff, and thank you very much for supporting Historic Stanton.
Very nice.
And I forgot to thank Dr. Tillerson Brown for hosting us this evening at Mary Baldwin.